Hello, and welcome to today's presentation, Groundwater's Role in Radioactive and Chemical Waste Transport. My name is Samantha Gentry, and I am an AmeriCorps
Yes.
member service program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement, which we accomplish through locally led education efforts and community engagement projects to address local conservation concerns. This presentation will be recorded and will be uploaded to Conservation Nebraska's YouTube page within a couple of weeks. So if you miss any part of today's presentation, would like to revisit any part, or share it with others, you will be able to find it there. If anyone in attendance is interested in speaking with a Conservation Nebraska member regarding conservation issues in Nebraska, or to find out more about what we do, please contact us at info@neconserve.org. I would like to introduce our speaker, Dr. Darryll Pederson, who has been involved in many groundwater studies in Nebraska and other places. In his professional work, he has been awarded the Distinguished Service Award for contributions to the science and the Geohydrology Division of the Geological Society of America. He was also awarded the Distinguished Service Award for his contributions to science and the International Hydrology Association. He has a PhD in geology and an MS in chemistry and physics. He is an emeritus professor at UNL with 40 years. And with that, I will hand it over to Dr. Pederson.
Well, thank you very much. And I want to thank Samantha Gentry for everything she put into this to get this show on the road and that. So I really thank you for it. The first slide is the taken on an outcrop on the Appalachian Mountains in Boone, North Carolina. And it shows what one phase of groundwater. The water is coming out of the pore spaces. As it comes out of the pore spaces in the rock, it freezes. And so it comes out as sort of little tubes like. This freezing action is a very important action of groundwater. The freezing action can break up the hardest rock because water expands when it freezes. And so on this face of the rock here, over time, these little ice crystals coming out and on the surface and in deep in, if it freezes deeper in, will slowly break up the rock into smaller particles like sand and gravel-sized particles, or even weather into very fine particles like clay and silt. But the main takeaway here is that this isn't an isolated occurrence. This occurs all over where groundwater comes to the surface. And so this mechanical weathering can break some of the hardest rocks down into much smaller particles. And these smaller particles then can be transported by streams into rivers, and they can form floodplains on rivers, which means you can have excellent aquifers develop adjacent to rivers, and we'd call that alluvial aquifers. Just one place doesn't mean anything, but if you have this repeated all over the Appalachian Mountains, it means a lot. It's weathering down the mountains. The Appalachian Mountains were once as high as the Rocky Mountains, but they're much older mountains, and so they're slowly weathering down. The second part that comes here is water is a universal solvent. It can dissolve many, many things. And so the groundwater can carry chemicals, it can carry even uranium uh, elements, because uranium is soluble in groundwater in oxidizing conditions. So we have this uh, step here in the Appalachian Mountains. Let's go to the Rocky Mountains and try to place the groundwater portion of the main water cycle. most of the moisture that we see in precipitation comes from the oceans. Uh, in the high mountains, it's much colder and it can come out as ice and snow. There are areas there where this can seep into the ground under the infiltration over on the left-hand side, seep down very deep or very shallow, and it can come out as seepage. We just saw one of these seepage faces in the previous slide. It can come out as springs, and with the springs coming out, it can create little rivers. Groundwater can discharge into freshwater lakes, and then down gradient, it comes back out again. And this is something we're going to see in the Nebraska sandhills. It can even discharge into the oceans themselves. Groundwater moves for the same reason that rivers flow off the mountains. The steeper the slope, the more gravity can accelerate and it can move particles down, first from the very little rivulets up, like where we saw on the first slide, into streams and into rivers, and it starts its journey off the mountains where it has weathered. Should point, and I didn't have a slide that would show the high plains of western Nebraska, but just think of the ocean as the high plains. The slope is much less when you get into Nebraska than it is in the steep mountains. You have the snowpack in the mountains that accumulates over the winter, it melts, and it provides a tremendous amount of energy to move these sediment particles down the slope and out into the slopes areas of Nebraska. Another slide on the left-hand side, a mountain type stream. They depend upon the velocity of the river water. It can transport gravel if it's not as much sand, and if it's very slow, like it's over an adjacent area, silt and clays can settle out that have weathered out of it. On the right side, we have just ordinary tree growing. Tree roots by hydraulic action can come out, expand, lift, and break up underlying rock. Things like moss and lichens can do the same thing through chemical type things. It's all about breaking it up into smaller particles so we can get the main aquifer material, gravel and sand. Water will move through clays and silts, but very, very slow. Picture a sidewalk alongside of this tree. The tree roots grow, lift up, bust up the concrete. That's common all over Lincoln. Another type of aquifer would be from lava flows, lava reaching the surface, flowing over the surface of the land. And when the lava stops flowing, it cools. As it cools, the top part cools first, but it also cools fast. This is buried later. It cools fast, and it can cool into a glass-like rock, or it could cool with a slower and have a few mineral crystallize out of it. But it continues to cool, and as it cools, the lava surface cools fastest and crystallizes into glass. Lower down it cools, but the glass then continues to cool, and as it cools, it shrinks and it develops large cracks in it. And you can see the vertical cracks in here. This represents secondary permeability and porosity. I get a kick out of labeling. They say impermeable rock, and they show secondary porosity in it. I will be talking about up at the Hanford site later in this talk, and these are the lava flows that underlie that particular site. The Niobrara Shale deposit in ancient oceans. You have cyclic depositions here. fine grain, slow movement, but we have this secondary process, permeability that water can move through very rapidly. So even the biggest rocks can be broken down, and although they're very low permeability, they can be significant. Uh, we have where water can dissolve limestone, and this would be a limestone layer. And on this part in here, if there's pollution up here, it can wash in, go down the sinkhole, go through the caverns that have been dissolved out by the groundwater. And this is very rapid. You do not want to get contaminants going down into a limestone aquifer because they can be transported long distances very fast. We'll go to Nebraska now and focus. This is the Niobrara River, or Platte River. As we look upstream in the distance, picture the Rocky Mountains. The river is flowing from the Rocky Mountains down the sides of the mountains and spreading out over the plains. It's carrying big loads during the fall or spring melt. This spring melt snow, accumulating snow, creates large amounts of floodwaters coming down into the plains that can carry all kinds of silts and clays, and particularly sands and gravels and even cobble-sized particles. Some cobbles are found in the base of the sandhills aquifer system. In this stage, it does not have enough water flowing to move all of the sands and gravels in the riverbed at this time. This riverbed probably has up to maybe 90, 100 feet of sands and gravels underneath it. Over to the side, on either side, it's very, very flat. This is the floodplain. When the river floods, the sands and gravels move, and over here, the water moves slower. The silts and clays settle out uh, and form layers of lower permeability. Another thing should be mentioned here too is rainfall in here can recharge the groundwater system. So at this point of time, it's probably the water being recharged by rainfall moving through this aquifer system into the river that is sustaining the flow. In fact, the Platte River does go dry in the summertime upstream of Columbus. Because its dependent flow is just on this. When it gets down to where the loop goes into the river, the loop is a groundwater fed stream out of the sandhills. So as we look at this picture, we see sands and gravels, but embedded in all of this are permeability layers, low permeability layers, silts and clays. And so the picture sands and gravels, on top of it silts and clays because the river meanders, then more sands and gravels, and then more silts and clays. So it's very dynamic type thing. And I'm going to go to the Nebraska Sandhills to uh, do this in a little more detail. I'm going to focus on the Sandhills. You have tributaries coming off the Rocky Mountains, carrying these sands, gravels, silts, and clays out. The slope decreases, and the slope of the general land was generally off in this direction to the northeast. At times in the past, sands and gravels were carried out into South Dakota. More recently, because the sands and gravels build up. When they build up in thickness, it means that the slope of the riverbed changes, and the slope of the riverbed can determine how much energy is available to transport it. Think of the slope something like this, 5 feet per mile. If you climbed up in a basketball hoop and hopped off, that 10 feet to the ground represents the work of gravity. Gravity can put a lot of energy into a system, but if the slope decreases, it fills up in this area, and then it backfills and backfills and backfills until eventually you get in the sand hills up to 1,000 feet of sand and gravel interbedded with silts and clays. Another thing I want to point out is this is the Northern Rockies down through here. It's much colder than the Southern Rockies. There's much more mechanical weathering producing sediment in the north of the Rocky Mountains, so there's much more sediment coming out into the high plains. Nebraska has probably the highest thickness of the High Plains aquifer, or the Ogallala that they sometimes call. As we go to the south, instead of having sands and gravel spread way out here, in Kansas, it's spread not nearly as far. And if we go down to Texas, they don't have nearly the thickness of the Ogallala aquifer and also the extent of it. The extreme weathering here contributes to it. This sand and gravel pile built up, and when it got high enough, it meant that these rivers coming down here were flowing on a very low gradient, and this was lower out here. And so the river broke through, and we think about the current Platte River and its systems coming out into this area of Nebraska. So it's working at building, I'll call another sand hills, taking sediments out into here. Look at sand hills more detailed. The black dots on this map are sandhill lakes. In this huge thickness of sand and gravel, the soils are very permeable. These are all sand and gravel deposits that soil some formed on, but not a lot. It's primarily sand. And so the rainfall in here is very, very effective in recharging the groundwater system underneath the sand hills. And where the rainfall's enough, the water table rises up to low spaces in the sandhills and creates sandhill lakes. These black dots represent sandhill lakes all through here. You notice there are many more sandhill lakes in this area at the headwaters of these rivers than there are close to the rivers. What is happening is these rivers, through groundwater sapping, have sapped their way headward into this huge aquifer system, and as it uh, goes in, represents a low area, and so the groundwater, instead of rising to the surface and having lakes, it's draining the water out into the rivers. These rivers are groundwater fed. There are no more rivers going straight through the sand hills. The only one you have is the Niobrara River that goes around it. In the extreme western part here, with the hashed lines, you have many, many sandhill lakes. This represents an area where the groundwater being recharged has raised the groundwater table to the point where there are lakes in all of these areas. But they aren't flow-through lakes like you would have here, where recharge goes through the lakes. I showed you some of these lakes, goes on and gets into a river. And so with the water coming up in these lakes all the time, so you have evaporation. You can't concentrate the minerals in there. And so this is an area of poor drainage and alkali lakes. You don't see many lakes in here because they're being effectively drained by these systems. These rivers merge and get into the Loop River system, which eventually gets into the Platte River system. I want to point out a unique thing that happens. Remember, the Sandhills Aquifer has layers of sand and gravel, silt and clay, sand and gravel, silt and clay in its aquifer system. I'm going to go to a spot on the Dismal River that is just upstream about where the E is here. There was a big sandhill lakes. the Dismal River was cutting headwards towards it. It got close to the Sandhill Lakes, and groundwater sapping created a channel so that big lake drained very rapidly. It cut down the Dismal River, and the sediment was carried out, and you can see the sediment accumulation if you look at the junction with the Middle Loop River. So it cut down very rapidly. So the deeper aquifer systems had lots of pressure because they were under all of this, and the deeper aquifer system under here experienced a blowout. Let's look at it this way. Increasing all maps like this have tremendous vertical exaggeration. Just think of these being nearly flat, way out into the sandhills, all the precipitation. You have a confining layer here, silt and clay, one underneath, unconfined sands and gravels, and recharge. Recharge on here, the unconfined can move into the lake, move out of the lake, and out to the stream. But down here you have a lot of pressure. The water is infiltrated, so it's a higher point, and that pressure can get through the silts and clays, but very slowly. So this has much higher pressure. So if you put a well down here, it would flow at the surface. What would happen if this stream suddenly had a huge flood from Sandhill Lakes? That stream would cut down. As it cuts down, now underneath the confining layer, that pressure's still there. You can have a blowout. That blowout, because the pressure just mobilizes the confining layers and gets up to where the stream was cut down. This is downstream on the Platte of the Dismal River. It flows from upper to lower here. It goes around this roughly circular object. This is one of those blowouts that occurred. The pressure from a deeper aquifer system when the river cut its valley down very fast caused this blowout of sand and gravel, silts, and clays, and it got into the Dismal River, and went downstream. You see water standing in here. Water is still seeping up through this big blowout, but it removed a lot of material in here that all was eroded and carried down by the big flood. In cross-section, it looks like this. This is the diameter of the spring on initial rupture. All kinds of stuff come up, and it eroded a drain down to the Dismal River at the lower level of it. Particles in here are in grain-to-grain contact. There's enough pressure to keep sort of a narrow conduit open to the surface, and then the sands in it are kept in suspension because the friction lifts the sand slightly. The one around it, you have grain-to-grain contact, you can stand on it. If you went in to this spring up here, the boiling sand spring, you would float if you stepped into it. The movies have it all wrong. Without the grain-to-grain contact, you would go down, but the density of the sand-water mix is such that you float in this mix. You don't sink. The movies have that all wrong. This is a conduit, about 150 feet deep to the deeper semi-confined aquifer system. And the students of mine are having a field day. They're floating in it. You can see how high they float because of the density. There's a freshwater surface right at the top that's flowing off into the river. They're standing in it. They have to balance, but they're standing in it. I had 3 graduate students on one trip down the Dismal River on a steep bank by one of these springs, held hands, and they went running and jumped into the spring itself. They disappeared. Their momentum carried down. They popped up like corks. sand everywhere. They did it 3 times and then decided they better get the sand out of their swimming trunks and everything before they would lose everything and out of their ears and hair and that. So one more thing I'd like to mention is that it's dependent upon the difference between the atmospheric pressure and the pressure in the deep aquifers. If the atmospheric pressure is lower, you have a lot more groundwater discharge. If the atmospheric pressure is higher, it sort of shuts it down. The blue pool, right where you get into the onto the river south of Mullen, uh, flow varies between 400 gallons a minute and 1,200 gallons a minute. 1,200 gallons a minute, low pressure, 800 gallons a minute, high pressure. And to switch gears a little bit, I'm going to eastern Nebraska. This is by the Mahoney Park, and this is Platte River. You have hints of a braided stream. Yes, it's still carrying lots of sediment, and but the banks are entirely different. And the reason the banks are different is an event that happened in Canada. In Canada, continental glaciers formed and they flowed to the south. As they flowed through the south to the south, they picked up rocks, they picked up everything, trees, you name it, and carried it because ice has a very rigid structure, and carried it to the south and into eastern Nebraska. Here you have a thick layer yet of sand and gravels, but it's the flow is not like it used to be. You know, the first slide I showed, the very wide ones, was when you had very high snowmelt runoff from the Rocky Mountains. So when people came into the area, they built dams and so forth to capture it for irrigation, for use of human consumption and that. So we no longer have these spectacular floods coming off. We can still have snow-generated floods, but not major. This till buried, coming down, buried, the Platte River's cut through it, but has buried all of the underlying river systems that used to flow out of Nebraska to the east into Iowa. So the till overlies it. And you have conditions, once again, of lower permeability, higher permeability. Hills have sands and gravels in them. So rainfall can get through, it can recharge. It can recharge in the high spots, and if it's the water that's connected down below, it can recharge a deeper sand aquifer. And that would be my next. Well, I'm going to show the rivers first. The glaciers came up, flowing down, and the greatest extent is about here. You can tell that this area is glaciated when you travel I-90 at the point west of Lincoln, where all of a sudden you get the original, that slide I showed you looking upstream, very flat topography in that. Glaciers went this far, and then the last advance, they'd retreat some, and the last advance are the solid dotted lines. You have the rivers coming out here, the Blue River, they couldn't flow against the glaciers, they flowed down here. When the glaciers retreated, they still retained this. But there was also other streams and, Platte-like streams coming down and going underneath here and into Iowa. If we go up to Hallam and go down to Beatrice and Sterling, Sterling has the main, from here to the east, has a main buried sand and gravel aquifer underneath the till that is very much like the in the sandhills, low permeability, high permeability, and so forth. At Sterling, Nebraska, you have one branch, and it goes underneath and up to Hallam, and the other branch from Sterling goes down north of Beatrice. So you have buried sand and gravel systems. And this is down by Cook, Nebraska. At Cook, Nebraska, if you go, the town was famous for flowing wells because the deeper aquifer system of this buried river system is being recharged through the till net, and it has a higher force or energy, so it is breaking through the tills and coming up. If you go down to Cook, Nebraska and go east out of town on that road, when you come to the bridge, park back from the bridge, get out, walk down the north side of it. This river flows to the northeast, the South Fork of the Little Nemaha River. And if you're by yourself, you may be lucky that it wouldn't be murky. But if the water's a little murky, if this is in September too, do it when the weather's nice because you don't want to get on a river like this when it's flooding or anything. It can get water from the surface coming in to it too. As we walk downstream, I'd have my students walk side by side downstream from the bridge, and eventually someone would maybe step into this. They were close enough. It'd be quicksand, but you know, the cowboy movies have it all. You don't sink totally. This is such a small one that you might just go down, with one leg. So it's a boiling sand spring coming up from a deeper aquifer. And take a copper pipe, push it down. Well, I should back up and say, if you feel cold water, walk upstream because this water comes from the deeper aquifer is colder than the river water, and you can find them that way too. Push pipes down different depths, and what these pipes represent is the sample of the pressure at a lower level. As the sand water moves up, it loses this pressure to grain, to the rubbing of the sand grains in that. You get a flowing well. This represents the pressure difference between here that we have and going down to the end of the pipe. These work because the sand boils out and the coarser gravel and stuff forms sort of a filter-like, and so you just have water coming out of the pipes. I'm going to change horses now. I'm going to go to eastern Nebraska, and I'm going to get into more chemistry, chemical type stuff. Lincoln Wellfield is here. Ashland is down here, the former ordnance plant, and Meade. The ordnance plant was a place where they loaded explosives into munitions starting in World War II and up to the present time. The Meade station up here, the Meade area, had a special type of ethanol plant and made ethanol from corn seed that was treated with herbicides and pesticides. But we'll first go to the ordnance plant. Now, the Platte River used to flow down here, sands and gravels and everything, but a river from up north that was flowing down through here had a tributary that cut headwards and captured the flow of the Platte River. So the Platte River flow was changed from going down through the Todd Valley down instead here. And as you look at the Todd Valley then, that is the classic floodplain like we saw on the slide looking to the west towards the mountains. Sands and gravels. Soils have developed on it, dust had flown on it, blown on it, but it still slopes this way. It still has recharge from rainfall, and it still has groundwater in here, and this groundwater flows down slope. So the groundwater from precipitation flows down slope towards here, but the Platte River now flows down through here. And so look at the ordnance plant first. This is RDX. It's the explosives that they put in the munitions. You had load lines in here. There aren't a lot of maps of that. It was probably deliberately so, but load lines, and that's where they would load the RDX, the explosives, into the munitions. But the thing is that this is sort of a crystal composite, like just think of sand or something that they're loading in. There will be spillage on the floor, and if there's spillage on the floor, you want to get it out of there because if you stepped on it, it's possible you could trigger explosion, and all the RDX in that load line would blow up. That's why they separated them too. After every shift, they would take hoses in. They'd use an industrial cleaner in addition, water hoses, and wash all the floors and wash it out the door. And it went out the door into the ground. This is permeable enough, got into the groundwater system, and the groundwater flow is about northeast to northwest. These are the plumes from those systems of here. We're probably talking about several miles long. Groundwater travels about a foot per day, depending upon the slope and the size of the particles. So you have this in here. This stuff is very bad for human health. You have people down here that live there, their wells have become polluted. And remember, it goes all the way down into the area of the Lincoln well field. Given enough times, the stuff will get out there, down there. It may be diluted some. So they're very busily trying to clean it up. So the RDX can cause health problems to people. The TCE is a same story. It's a powerful cleanser, but it's also, you don't want to drink it. You don't want cattle to drink it and so forth. And this is the plumes of the TCE coming down from the different load lines. They quit munitions work there, and you have to clean it up. You got to get that stuff out because it's going to continue to move on down. Groundwater is going to transport it. So, but the only way you can't dig it out. This is down in the groundwater system. So, but the only way you can do it is to put one well. There are many wells actually. One well on this side and another well on this side of the plume. At the depth, screen them at the depth of where the main water plume, contaminant plume is at. And as the pump water down here on this well and on this side, you pump it out. You create a groundwater flow this way through the plume, and the water you pump out of the well, you remove the contaminant. That's the way you get rid of it. It takes about 100 pore volumes of water moving through a pore to clean one pore. So it's a mammoth project. They're working on it. It's been still going on, making good progress. The Mead Field plant, ethanol plant. And this was a little bit different type of a situation. This is ongoing. And if you want to follow the history of what's going on in the last 10 years or so, Chris Dunker with the Journal Star has written some excellent articles in the local newspaper, Lincoln Journal Star, about this plant. They have worked and worked on it. Dying bees and so forth showed up, cleanup. Seed suppliers took over cleanup. All of the major seed companies were sending their herbicide, pesticide treated seeds, corn seeds, to this plant because it was thought that the ethanol process would destroy these chemicals. It didn't. They have a wet cake that they call it, and this wet cake They had a spill of water that's contaminated. This is all above this major Platte-like aquifer system. They are working on it yet, and like I said, it's a work in progress. All the major seed companies got together to clean it up. They're paying for the cleanup costs, but they're having troubles. It isn't working really well. And as I mentioned, Chris Dunker of the Lincoln Journal-Star has some excellent articles on it. So this is a work in progress. Switch horses a little bit again and talk about radioactivity. Uranium-235, uranium-238. Uranium-235, both of the uranium isotopes were made about the same time, a very long time ago, but one of the isotopes is much more radioactive than the other. And the U-235s is very radioactive and is what they look for bomb material. The U-238, well, that's a little bit of a problem. Maybe you can make some uses, and they did. The original, they talk about enriching uranium. What they're talking about, they're trying to extract the U-235, but it's only about, in natural occurrence, only about 0.7%. So they use various techniques. They use spinning, uh, they spin it around real fast, high-speed centrifuges, more recently. It's a difficult thing because these two isotopes have the same chemical characteristics, so it's difficult to work with. One of the original, several of the original bombs that were used, well, in particular the one in Hiroshima, was the uranium-235 bomb. They very rapidly discovered something, and I could elaborate more, but thank the Norwegians, give them a cue, and if you can put 238 in a reactor, nuclear reactor, and 235 in it also, and you control the flux of the neutrons correctly, you can convert the U-238, which is low radioactivity, in plutonium-239, which is very radioactive. Half-life of 24,000 years. What's a half-life? How long half of the original to undergo radioactive decay? It's a man-made element. It also has different chemical characteristics than uranium. And so it's a chemical separation, and chemical separation usually involves fluids. So before I go any further on that part, I'm going to just interject. Nuclear power plants have control rods, they have extreme high pressure, they have to have heat exchangers, they have to keep this reactor cool. Control rods will reduce the reaction in there, but this stuff is still naturally radioactive, still generates heat. A nuclear power plant has to be continually cooled, even if you put the control rods in, because these things are all still radioactive. If you don't keep them cool, you have a world of hurt. You have the Chernobyl plant. They lost the cooling cycle in there, couldn't get the pumps going, couldn't cool, and melted down. Melting down is the worst thing that you could possibly have happen. So you have to keep it cool all the time. Different ways of cooling. You have the towers, you have from rivers or lakes, and the Fukushima reactors in Japan, an earthquake caused the loss of power lines coming in. They lost the power of their generators because the tsunami wiped them out, and in turn, their reactors melted down. There was really nothing they could do about it. And this will be an operation that goes for a very long time. But it's very important. Even the spent fuel rods generate a lot of heat. And most of the spent fuel rods are still at the plants around the world in swimming pools where the water can absorb the heat and get rid of, the heat that's being generated. And it can also reduce the radiation from the radioactive spent fuel rods. Uh, another type, there's another type of plant. If they change the configuration a little bit, they can leave the U-238 in there and convert it to plutonium-239. And that's what they did at the Hanford. It'd be called a breeder reactor. It makes more fuel than what it consumes. And plutonium-239 can be separated easier. It doesn't mean it's safer, but easier. There's one nuclear plant that was in history that was down by Holland, and it used liquid sodium to cool and a graphite moderator. It was located there because there was an existing coal-fired plant. They had the power lines to take the electricity away, and also you had good cooling water available, including one of the buried uh, aquifer systems I talked about earlier that we saw down around Cook. This is a tributary of it. It started leaking liquid sodium. There's no way to fix these buggers because the radiation is so intense. You can maybe be around them about 20 minutes, and that about or 4 minutes, and that's about it. They removed all the radioactive material they could remove, and they put it in, took it someplace. I don't know where they took it. They tipped the reactor vessel over into a hole that was dug, put low permeable material around it, and covered it with a concrete cover, continuing to monitoring it to see if there's any leaks. If there's leaks, there's going to be a lot of money involved. Okay, so these spent fuel rods and everything represent a real issue. Radioactive waste disposal. 1 barrel of radioactive spent fuel rods generates as much heat as a clothes dryer. If you took a bunch of barrels and buried them in the ground, the heat would build up and build up and build up. Eventually they melt. So this waste has to be kept cool, in addition to being separated from the environment because it's soluble in water. It can be carried away from a storage site and get into areas where people live or into their groundwater wells and that. No good site has been located yet. Going into the Hanford site, there they had the breeder reactors. All of the breeder reactors were through here. And they produced plutonium-239. And in fact, at this site, they produced plutonium for most of the more than 60,000 weapons built for the U.S. arsenal. They got way ahead, so they stopped using them. But there was a problem. They could create the plutonium-239 in a breeder reactor, and chemically they could separate it. But what they had was plutonium, and then they had a liquid mixture of highly radioactive material and what to do with it. They thought they had one thing going for them, and they had big, heavy glass jars, and they filled them with the liquid, and they sealed the top on them, dug a long, deep trench, and separated them so the heat wouldn't build up, covered them with low permeability material, and then called a bulldozer operator who wasn't privy to really what he was working with to build a mound over them to even secure more. Well, it turned out the bulldozer broke the glass, And so you had that immediately get into. And what is the groundwater system? Sort of black. These are lava flows. This is the Columbia River. Remember the secondary permeability in the lava flows? Easy path to here. This country now, at this point, trying to clean up this site, employs about 10,000 people and about $10 billion a year. They're still working at trying to clean it up. It's gotten into the river, it's went downstream, it's affecting people. So we have to have a very dry place to put it, and it cannot have water moving through it. They thought they found it at the Yucca Mountain site in Nevada. But the Yucca Mountain site, it had it had no permeability. It had pore spaces were zilch, and it was thick. It was in a very dry area in the Yucca Mountains. Just think desert above, so you don't have a lot of rainfall that could possibly screw up things. And the groundwater table was some 550 feet below the surface. Because it was below the surface that far, it was thought that this rock unit would be dry, that there wouldn't be any water moving through it. The second thing is they could cut tunnels into it. They could excavate large caverns to put the nuclear waste in. They could dissipate the heat through the walls of the large uh, uh, caverns that they formed. And they were really going about, they thought they had the problem solved. Well, the trouble was that the wanted base level on the chemical compositions in the groundwater underneath this, so that if there was a change, they could detect it. Upon doing this, they found out that the groundwater had man-made chemicals in it, recent man-made chemicals. And let's just throw out the Viagra comes to mind. And how did it get down there? There has to be secondary permeability. There has to be water moving down to the aquifer, that very deep aquifer in this area. Up in the mountains, so they stopped that. The site has to be dry. It has to dissipate the heat. Uh, Denmark thinks they found it, but it's in the permafrost, deep rock, solid. But they are not considering it because there's possible issues with it. There was one low-level radioactive site attempted to be located. This would be radioactive waste from hospitals and manufacturing firms where they measure thicknesses of something by the amount of radiation that comes through with that radioactive thing. They formed the 8 states, some 8 states formed the compact to locate and build a low-level radioactive waste site. Nebraska was U.S. Ecology did the work on siting and that, and they located a site in Boyd County that would be potential for the several central U.S. states. Uh, in order to get a license to build it, they had to demonstrate what the site performance would be, how they would handle and everything, and the site characterization. What is the geology? What's groundwater movement? What's the flow around? What's the temperatures? Anything to do with that. Well, they worked it up, submitted a license application with all their findings, and it was rejected because there were issues with some of the things with site characterization. They went back to the drawing boards and worked up more, did more tests and stuff in the area, submitted another license. That was rejected, submitted another license. Uh, I think it was 5 or 6 that they gave up. Nebraska kept rejecting them because they hadn't had the analysis that could prove it was a safe site. There was a legal fallout from that later. Nebraska originally paid $145 million in settlement to end the dispute, ending Nebraska's participation. It followed the court trials real carefully. I was on the review team for the license application, and we were never called. It seemed from the papers that they focused on a woman taking some papers home to her house that she shouldn't. Also, another comment, and I can't prove this because I heard it. Several years after they abandoned the effort, the locals had a uh, very, very heavy rainfall and stuff, major flooding on Zizzy Creek went down through the valley that the site was located in. They had canoe races. Well, I appreciate your attention and everything, and I'm going to turn it back over to Samantha Gentry, and she will address anything that you might have. One last look at the sandhills. Samantha?
Yes, thank you so much, Dr. Pederson, for sharing your time and expertise with us today. If anyone has any questions, please email Dr. Pederson at dpederson2@unl.edu. Have a great day. Thank you.
Thank you.